Okay, section 1.1, vectors in n space. You have learned the vectors from two-dimensional or three-dimensional vectors in the earlier years. Now we're going to expand those concepts to the n-dimensional spaces. Some of these earlier lectures can be viewed from these YouTube movie clips, and also these lectures from I have made this as a lecture note on the web that you can see the definition of the contents of our book in Korean, and also the problems and solutions and the computational tools as well in here. So you may go through it if you like to go through lawfully before you come to a class. Okay. Okay, there are all the code and the informations, definitions, theorems, and examples, and computational tools all together in here. But in this semester, we're going to go through it in English with the new English version of my linear algebra book. Okay, in this section 1.1, we will introduce the definition of a vector and the property of vectors. First, a vector is a geometric quantity described by a magnitude and a direction. Okay, we will start with the concept of a scalar in here. Scalar is one that can be described by a single real number. Examples include the length, area, mass, or temperatures, etc. But vector is a geometric quantity described by a magnitude and a direction. Two things. Examples include the velocity, changes in motion and in position, and pose. A vector can be sketched as a direct line segment like this in two or three dimensions. Like this. A vector from our initial point A to the terminal point B can be written as an arrow like this, and can be written as a bold letter X with this initial number, initial point, and terminal point with the arrow marks up there. Okay, a vector with the same initial and terminal point with magnitude 0 is called the zero vector. Zero vector. Okay, if those two points are same, then it is called the zero vector. And these are the examples of vector field consists of vectors. So as you see, it has a directions like this. This is a vector field, example of a vector. Okay, from now on until the chapter 9, before chapter 9, we will use only real numbers for scalars. Then, and the scalar k, this k will stand for the scalar in a real number r. But from chapter 9, this scalar will be expanded will be generalized to the complex field and other general vector field. Okay. As you know, the vector addition and scalar multiplication will be defined, and parallelogram laws are used for the vector additions like this. And these are what you have seen in high school days, and we will expand it to the n spaces. In R2, which is a real coordinate plane that you are familiar with, in here, if vectors have the same magnitude and the direction, then even if they are different, they are in different positions, we regard these vectors are equivalent, and the vectors in R2 can be written as this or this. These are two same notations. And these x1 and x2 are called a component of vector x, bold x. Two vectors x and y in R2 is called equivalent if x1 is equal to y1 and x2 is equal to y2. If they are component-wise same, then we call these two vectors are equivalent. And we write two vectors are equal. Okay, here in figure 5, this vector from O to Q prime and the vector from P to Q, those vectors all can be written as y1 minus x1 and y2 minus x2 when P and Q are given in this way. In this case, as you see, these components are all same. PQ, component of PQ and component of OQ primes are same, so these two vectors are considered equivalent or equal. Those two vectors looks different, but they have the same magnitude and same direction, so these two are same vectors. Okay, we'll see the examples. If we define the point 0, P1, P2, Q, Q1, Q2 like this in R2, then let's express the vectors OQ and PQ, P1, Q1 and P2, Q2 in component form. Okay, so OQ vector is how? Q is here. So OQ vector can be obtained by 2 minus 0 and 3 minus 0 as each component like this. P1, Q1 vector can be obtained as 2 minus 0 and minus 1 minus 4. So it's P1 or Q1 can be found as 2, 3 like this. This is same as OQ1 minus OP1. And and also the PQ and Q2 also can be obtained by Q2 minus P1. So minus 1 minus 1 0 at the first component, minus 1 minus 3, and 4 minus 1 in here like this. As you see here, OQ and P1Q, Q1, and P2Q2 vectors are all consist of two components, 2 and 3, which means these three vectors are all same. They are all equivalent vectors. This example shows it. Okay, anyway, you can do the practice in here at Chrome or Firefox browser to practice. To compute the vector OQ and P1Q1 and P2Q2 like this. As you see, so I defined the each point in R2, and I did compute these three vectors. And as you see, these three vectors are all same. That shows they are all equivalent vectors. if you change the vectors like this, then you will see the different vectors that has different meanings in it. Anyway, okay. So if you are asked to compute the vectors in a component form, then yeah, you can do it by your hand, or you can use this code written in Sage or Python. Okay, and the sum of two vectors, x plus y, and the scalar multiple of x by scalar k are defined in this way: the component-wise addition and component-wise scalar multiplication in R2. And zero vector can be written as 0 and 0. And this is a property of zero vector. By adding the zero vector on any vectors doesn't make any changes. And x plus the minus 1 scalar multiplication vector will make zero vectors. And in this case, this scalar multiple minus 1 of x, it can be written as minus x, and we call this minus x is the negative vector or additive inverse of the vector x. We can do the computer simulation of this scalar multiplication and vector addition on this website that you may try. And if I show you one copy. For example, this is for example, this is a simulation tool to show how the vector addition and scalar multiplication can be given. If I give two different vectors, then it will give us addition of two vectors that shows this. We can even change this by this that shows the vector additions and simulation of it. And also, this also can be done by Sage comment like this. If we give a different vectors, then it will give us a different output of it. And vector sum, and define a vector, and addition of two vectors. And also it has a lecture note in it, and also explanation of
자, 1장 벡터
be found on those websites. Those are all in these books that you can use it. Anyway, so as you see, if you two vectors were given and asked to find the scale vector addition or scalar multiplication, all you have to do is just to do it component-wisely. It can be easily done. And also, you can do the same thing with the code that you can utilize on these two and many other websites that we can use. If you change the numbers, then you will have a different things. The reason that we are learning this is this work not only for the vectors in R2, it also can work for the vectors in high-dimensional spaces, such as R5 or R7 or R100. Anyway, so now we going into the three-dimensional space, like this. R3 represent for the whole vectors with the three components of scalars. The three tuple of real numbers is called the vector in R3, and it can be written as this. Okay, and likewise, the x1, x2, x3 are called the component of vector x. Two vectors are equivalent if each component are same, and with those concepts, suppose we have the vector zero vector and P1, P2, Q, Q1, Q2 in R3 like this, we can express the vectors OQ or P1, Q1 or vector P2, Q2 like what we did. For example, P1, Q1 can be found by Q1 minus P1. That means OQ1 vector minus OP1 vector, which says 2 minus 0 here, and minus 6 minus 4 here, and 6 minus 2, which is 4, is here. So P1, Q1 vector can be found as a 2, 3, 4. Similarly, P2, Q2 vector can be obtained by PQ2 minus P2. So minus 1, minus 3, minus 1, minus 3, which is 2. 4 minus 1, which is 3. 4 minus 0, which is 4. So as you see, these three vectors, OQ, P1, Q1, and P2, Q2 are all equivalent in R3. The same thing can be done with the three-dimensional vectors like this in R3. Okay, the definition of vector addition and scalar multiplication for the vectors in R3 can be done similarly, like what we did. And zero vector in R3 are defined in the similarly, and negative vector of a given vector are also defined in the same. Okay, this is what you have treated so far. Now, we expand this concept to the n-dimensional space Rn. Okay, the Euclidean space R2 and R3 can be generalized to n-dimensional Euclidean space Rn as follows. Rn stands for the set of all vectors with the n components like this. Rn is also called the n-dimensional space, and the elements of Rn are called the n-dimensional vectors. Okay. In chapter 9, we will have a rigorous explanation and definition and proofs for general vector space. But now we just start with the Rn. Okay, the n tuple of real numbers like this is called the n-dimensional vector and can be written as this. Okay, n by 1. This does. And the real number xi's are called the component of the vector x. The two vectors are called equivalent or equal if each component are same for all. And vector addition for two n-dimensional vectors and scalar multiplication of n-dimensional vector x by scalar k can be defined in this way, like what you did for vectors in R2 and Rn. The zero vectors has a property that you already familiar with. And negative vector is defined similarly. Okay, with the vector in two vectors in R4, we can compute the vector addition and scalar multiplications without much difficulty, because all we have to do is do the computation component-wise. And those computations can be done not by only hand, but also by using the computational tools. And the vectors in Rn has the properties like this. Okay, vector addition is commutative, and vector addition is associative, and zero vector has the property that you already saw, and negative vector has the property like this, and associative rule are hold for vector addition and with the scalar multiplication. And the proof of this theorem is very simple, and which can be found in here. Which can be found in many places, and also you already knows. Here. Okay. Yeah, the property of vectors, and these are the properties that I introduced to you, and these are the kind of detail of the reason why they hold. It's just a simple computation to check. Only difference is it works for the vectors in n-dimensional space. That's the only difference. But all the process of reasonings are same as before. Okay. And the next property of the vectors is this. If we multiply scalar 0 on a vector, then it's going to be a 0 vector. And scalar multiple, any scalar multiple over 0 vector is a 0 vector. And if you multiply scalar -1 to any vector, then it will give you a negative vector of that given vector x. Next definition is, I think, is the first important concept for you to have. Linear combination. For vectors, v1, v2, and vk's in Rn, if we write the c1, v1 plus c2, v2 plus plus ck, vk with a set of scalars, ci's, then we call this vector. This is the scalar multiplication of and the addition of k vectors. This which can be considered another new vector x. This vector x or this vector is called a linear combination of vectors vi. So this is a definition of linear combination of given vectors. Suppose you have k different or same k different vectors, then you can always generate a many linear combination of those given vectors. Okay, linear combination concept. Okay, so suppose we have these three vectors in R4, then we may find a linear combination of those three vectors, which is 2x minus 3y plus g. Okay. How are you going to do that? It's a very simple hand calculation that you can easily find as 13 minus 10 minus 6 and 1. Just multiply 2 and multiply minus 3, and then just try to add all three, which gives us this. This can be done in this like this. Define three vectors x, y, and g, and print 2x minus 3y plus g. Then you will see the answers like this. If you change the vectors, then we have like this. Then you will have another linear combination of given three vectors. If you expand it to the fifth dimensional vector, like this, then you will have a vector in R5, which is a linear combination of these three vectors in R5. This can be done for any vectors in Rn. So you now at least you can do you can make any linear combination of given vectors as you need it. This linear combination is a very important concept that I will explain. Okay. Here, from the above, example 5, and this can be done in the stage as follows, like this. We build up the relevant vectors and give the command to do a linear combination of these vectors as many as you need. Then if we combine all these together, then we will see such as this. We define x and y, x, y, g, x, y, and g vectors like this, And if we define xyz as a vector and 2 minus 3, 1 as a scalar like this, then this computation also can be done with this command, which is another command to produce a linear combination of given vectors. So there are many ways to deal with it in Python and Sage. Okay. We can create an applet to generate the random vectors and scalar and find the linear combination as well. I may show you this one. This is a website which was made by one of my friends in Washington State, and let's see. Okay, here, this shows you some concept of linear combinations. Okay, linear combination, this explains how the concept of linear combination, and this gives us the examples of the linear combination of given vectors. He gave 4 vectors and tried to find the linear combination of those 2 given vectors in this way. Then this gives you the linear combination of those. If you change the condition, that will give you the different answers. And also there are many. There are vectors that defined, then multiple scalar computation, and also it gives you the space to compute. So there are many ways that you can exercise what you have learned in here. I think that, and also I gave you some reading materials here to look it over. I think that's just a brief review of the vectors that you have learned and to introduce the general form of the vectors in Rn. Any questions?